Okay, so welcome everyone to the second lecture for this course. So the first lecture was more of an introductory lecture where we discussed the logistics. This lecture we start to get into the core material for this course, and in particular we're going to start to talk about some multivariate data setups, and in particular we'll start our discussion on multivariate regression. So just to make a couple of like a quick announcement is that homework one has already been posted, and that's due on September 24th, and that'll focus on material that starts with today's lecture. So today's lecture is really kind of the beginning of the core material in this course. So just to give a brief outline of what I'll be covering today. First, I'll be introducing the general framework and a very simple example where we use this general framework just to kind of put most of the discussions that we focus on into a particular context, and I'll talk about it shortly. Then I'll briefly review simple linear regression in the context of this general framework. And simple linear regression is hopefully something you've seen that's not really multivariate per se. And then we're going to move on to multivariate linear regression, where we start to see, potentially the influence of having multiple variables. So just to remind people, so the scenario we're in is where we have multivariate data, and this is a reminder of what we covered at the end of the previous lecture. And there's two settings that we're going to focus on in this course: the supervised setting, where you observe some underlying label y, and then the unsupervised setting, where you just observe p variables with no label. And so here there's two key things. There's the sample size n and the number of variables p. Now I'm going to introduce this general framework for this course, which I'll keep referring to, so you can think about this general statistical or data science framework that we'll be trying to put most of our discussions into this context, just because I think it helps us ground things a little bit. So the general framework is going to have four components. And as I said, we're going to first illustrate this with an example, and then I'm going to keep coming back to this framework. So the first thing is the data, and so what data is observed. The next thing, which is something that we'll introduce, is this notion of a statistical model. And a statistical model is really useful because it allows us to discuss, to firstly determine how the data is generated. Usually you don't know this exactly, but if we start with a statistical model, this allows us to kind of discuss various properties that we'll see shortly. The next thing is an estimator or an algorithm or a set of algorithms. And so this is just a function of the data that hopefully tells us something about our parameter of interest, which we'll talk about shortly. And so the statistical model also has the parameter of interest. Sorry. And so the final thing is what inferences can we draw from this data. So I'm going to illustrate this with an example, because this is all pretty abstract at this point. So let me illustrate this with a very, very simple example. So we're going to look at the mean of independent normals. So here what we have is, if we look at component one, which is just our data, essentially we just have the simplest case where we have this scalar random variables here, and we have n samples. So here you can think about this as being unsupervised, because there's no label features, and then we just have that p is equal to 1. So this is kind of not actually multivariate at all. The purpose of this example is to focus on something that hopefully you guys are familiar with, but to illustrate how we use this statistical framework. So the next thing Okay, so we're going to look at the statistical model with unknown parameters. Okay, so sorry, let me just... And so because we have a normal random variable, we're just going to say these xi's are normal with mean mu and variance sigma squared. And so we'll say that and so the goal here is to estimate mu. So I should say we have n independent samples of a normal with mean mu and variance sigma squared. We're gonna the goal is to estimate mu and then assume that. And so this is a very canonical example in statistics. And for those of you who've seen 310 or something equivalent, this is a very sort of simple setup in 310 where we're looking at trying to estimate a mean parameter from sample data. Okay. So the next thing is the estimator or the algorithm. And so what do you think would naturally be a reasonable choice of estimator if our goal is to estimate the population mean mu? So hopefully a lot of you are thinking that that would be the sample mean. Okay, so this is again, this is a function of the data. The data here is x1 through to xn, and we're just taking the mean of that. So it's a function of the data, and we're hoping that that tells us something about the unknown parameter of interest. And so the next thing, which is okay, so the next thing is, what does, the sample mean tell us about mu? And this is really what inferences can we really draw from this x bar with respect to mu? And so in this case, it's pretty easy and nice. It won't be that easy for a lot of this class because we actually know what the distribution of x bar is here. It's we know that x bar has this normal distribution with mean mu and variance sigma squared over n. So we can certainly say that x bar will certainly converge in probability to mu. And then we also know that the variance of x bar is sigma squared over n. And certainly the expectation of x bar is sigma squared over n. And we'll even know its distribution. So, therefore, so we can find confidence intervals or do any other inferences. And so this in some sense is the easiest case where we actually can easily determine the distribution of your estimator or the output of your algorithm. And as we'll see in many of the examples that we come up with in this course, it won't be quite as easy as that, and we'll be using various other kinds of analysis tools and measures for that. But this is just illustrating kind of the 4 key components of the framework in this very simple example that hopefully a number of you have already seen before. So now we're going to build up towards multivariate regression by considering simple linear regression here. So this is the case where, again, something you've hopefully seen before, where you only have one x variable and one y variable. So your data here is okay, so this is going to be supervised. And then, once again, we have p equals 1. So you can think of this as sort of the next level of complex after the sample mean, because now we have two variables and we're kind of trying to fit the relationship between them. So, and we're going to use a linear model to try to fit that. So this is our data, which we've already given. So that's really the first component of our scenario. The second thing, which is a statistical model, this is something where, once again, because we're doing simple linear regression, it makes more sense. It makes the most sense to typically assume that we have a linear model, because that's the way that we can assess how our estimators are doing. So if we had a nonlinear model, it would make more sense to maybe use a different type of regression. But here we're going to use a linear model, which is widely used and what we use for linear regression. So we have that yi is beta 0 plus beta 1 xi. And then very importantly, we also have, some noise, because if there was no noise here, then basically we'd just be saying that, that you can get a perfect linear fit and there's sort of no uncertainty in that. But like in all statistical models, we need to assume some kind of uncertainty. Otherwise, it's more of just a kind of a mathematical model rather than a statistical model. But as always, we need to make some assumptions on this. So epsilon I. So this is I equals 1 to up to n. Epsilon I here is zero mean. Zero mean. So what that means is that this is okay. If it was not zero mean, this wouldn't make a lot of sense, because you could just add that mean to the beta 0 intercept term. So that's why we're assuming zero mean here. And then we assume that so what we have in this model is that beta 0 is intercept term, and then beta 1 here is the slope term. And this is really the standard statistical model that we're going to assume for linear regression. So if you've seen linear regression in the past, it may not necessarily present this as a model. It may just kind of tell you how to calculate kind of an intercept and slope terms, which we'll talk about shortly. But I mean, like when we get to the fourth step of doing analysis, we can't really do this meaningfully without a model. Okay, so what you can hopefully work out is that the intercept term, the property of the intercept term is it must ensure that it goes through the point x bar y bar. That's something you hopefully remember from the regression line. and and therefore it satisfies this equation for beta hat 0. And then for beta hat 1, again, if this isn't familiar to you, you can look it up. What we have is this is just equal to is equal to rho hat. Let me just write it this way. Okay, and so let me just define what these are. So there are 5 key statistics that you can derive everything from when you're talking about bivariate linear kinds of fits, and this is related also to the bivariate normal, which I'll talk about in the next couple of lectures. Okay, so this is something that you can look up. I'll talk shortly about how you actually derive this expression. But this is this is essentially what we can calculate for the parameter estimates, and so the analysis is something we'll see shortly in a special case. And the questions we're really interested in is okay, so first what I want to do is to give you a least squares perspective, and some of you may a least squares perspective here, which is just that you can interpret beta hat 0, beta hat 1 as the solution of an optimization problem. Where you're trying to minimize the least squares. And so the way to kind of think about that is that, you observe your data, so look X and Y, and let's just say you have your endpoints that kind of sit, just somewhere like that. That's your data. So each of these points is just an xi, yi. And so what you're trying to find is kind of we'll draw like what we think might be a line that sort of goes through these points, where if you look at the distance between if you look at the distance between this line and all these points, you effectively just want to minimize that distance. So we want to minimize the square distance from whatever line you choose to those endpoints. Okay, so. Okay, so this is where I'm going to kind of pause very briefly and just give you guys a chance to think. It's good to get your hands dirty with these calculations because that's what you'll be doing on the homework assignments and then on the project. This is going to be kind of the first big calculation or first calculation that we do, and some of the steps will really carry through this lecture and for the rest of the course is how do we actually calculate beta hat 0, beta hat 1 here. And, the expressions you've already seen, but now how do you actually get to those expressions? And the least squares perspective kind of gives you a way to get there. Okay, so if I were you, I would pause the video right now for about 5-10 minutes and have a go at trying to think about how you would actually calculate this. So I'd say so we're going to pause and come back after thinking yourself. And for some of you, maybe this is a very easy question. For others, it's good to just make sure that you recall how to do this. Okay, so hopefully you've had a chance to stop and think about this. So So this is hopefully simple enough, and you just think about, to minimize least square, what you basically do is it's just a calculus problem. So we want to differentiate and set to 0. So to do that, we basically just differentiate with respect to beta 0 and respect to beta 1. So if we look at if we differentiate this objective with this least squares objective with respect to beta 0, what do we get? We basically just get that we have a constant in there, so that just leads to that the sum should equal to 0. If we look at this, like if we differentiate what's inside, there's a negative here, but that doesn't really matter because we set things to 0. And then if we differentiate with respect to beta 1, what we're going to get is that we're going to get a pretty similar expression, but instead we're going to see an xi here because there's an xi in the squared. So we're going to get okay, and so then that should equal 0. So now if we put that together, then so we'll call this equation 1 and equation 2 here. So from 1, we actually get exactly the first expression. So we can see that if you do some simple manipulation, you get that y bar equals beta hat 0 plus beta hat 1 x bar because you're adding everything up and then you can divide by n, and so you get that first expression that beta hat 0 is equal to y bar minus beta hat 1 x bar. And then now we can plug that in to the second expression, and that's going to give you so then we get that if we plug in beta hat 0 equal to beta hat x1 bar like this, we get this this expression equal to 0, and then we get some kind of nice this should be a plus. And then we get that okay, and then if you continue with these calculations, and I'll let you kind of fill in the gaps there, you'll end up with that beta hat 1 equals over sigma hat x. So I'll just say continue like that, and I'll let you to continue this calculation. So what we've done here is just shown how we get those, how we actually calculate the beta hat 0 and beta hat 1. And it also gives you the perspective of these linear regression calculations from least squares. Okay, so the analysis is generally, this is something where it's going to be a little bit subjective what we actually do. I'll define some precise metrics for this shortly, but I just want to kind of give you a little bit of perspective here. So what does beta hat 0, beta hat 1 tell us? And so what we're going to do is we're going to simplify by standardizing variables. Okay, so what we mean by that here is we assume that and this is something you can easily do with any data set that you get, and it's often recommended, is that you always standardize your data to begin with. Okay, so what that means is you just subtract off the mean, which means that x bar equals y bar equals 0, and then you also divide by the square root of the variance, which means that sigma hat squared equals sigma hat y squared equals 0. So in this case, what do we get? In this case, what we get is that beta hat 0 is just 0, so no intercept. And then we also get that beta hat 1 is equal to rho hat xy. And this is just the sample correlation, so the correlation. So the line you just get here is just you may have heard this expression, the correlation line. So what this tells us is that when p equals 1, we have that the regression coefficient of the slope is just the correlation. So one way to interpret this is that okay. So in the case where we've standardized the variables like this, we have that the regression coefficient and the correlation coefficient are actually equivalent. Okay, so this is kind of pretty cool and interesting, and some of you may already be very familiar with this result. And so you always just think about, regression, just basically the regression coefficient may basically being a measure of correlation. We'll actually see what happens in the multivariate case in today's lecture. Okay. Now we're moving on to kind of the main topic of today, which is multivariate linear regression, which is a very widely used technique. And we'll see that it, in some ways, it follows naturally from simple linear regression, where you just have p equals 1. But in other ways, we're going to see that some interesting things come up, which are different in the multivariate case to the simple linear regression case. So in the multivariate linear regression case, we have that our data is just the supervised data this is supervised, so there's a y here. Okay. And here we have a linear model. So we have that, again, we're going to try to follow the bivariate or the simple linear regression case as much as we can to begin with. And so the natural choice for the let me just we're going to start actually with the simpler setting where so we're going to start with a setting where our data is perfectly centered. So we have that so we're going to center all our variables. So x bar 1 equals x2 bar equals x p bar equals y bar equals 0. And then we also have that so we're doing the typical standardization you typically do, because we're going to see shortly that makes our calculation much easier. So just to be clear, we have that x bar j is just the sample mean. Okay. Okay, and then okay, and then we have that this is the sample variance, and you hopefully so we're kind of assuming that everything's centered at 0. Everything's centered at 0 and normalized to be 1, and you can transform the data like this pretty easily in your in your class project, and in some of your assignments you'll be required to do this. And we're doing this just because it allows us to state things more. It simplifies the calculation a lot. So the next thing we'll talk about is the statistical model. So this is the linear model. So once again, just notice that I'm just really referring back to those components of the framework. So we're talking here about the second component, which is the statistical model. And so we're going to, again, mimic what we did in the simple linear regression case. What you'll notice here that's different is I don't have an intercept term, and that's because I've already centered the variable. So the intercept term should just be 0 here, which it is. because you saw that in the simple linear regression case, once you center, there's no need to really to have an intercept term. And once again, we have a noise term here. So we have that the expectation of epsilon I is 0, and then we have these beta 1, beta 2 up to beta p, their regression coefficients. Okay, so that's going to be the model, and we're going to either get to in today's lecture or on the following lecture, we're going to understand, we're going to relate back to this linear model to determine, how good, what kind of, like how well our estimators, which I'll discover shortly, are performing. Okay, so now I'm going to talk about the estimator, the algorithm. And so what's a way that we can potentially generalize what we saw in the simple linear regression case to the multivariate regression case? And that was where the least squares perspective that I introduced is pretty nice, because what it does is it gives us a pretty simple way to generalize, where we can say that our estimators of these regression coefficients, so these are the parameters of interest. We can simply interpret this as the solution to the as the minimizers of this least squares objective. Okay, so we're just going to minimize least squares like we did in this case, and we're going to get back to analysis shortly. What we're going to see as we go throughout the course is that we need to discuss sort of components 3 and 4 in a little bit more detail each time. So typically component 1 and component 2, we pretty much just assert from the beginning. And then components 3 and 4, we're going to spend a lot of time kind of discussing the details of that a little bit more. So what we're going to do here is just try to get some understanding or interpretation of what those estimates give, and how we can potentially relate that back to the original statistical model. And so what I'm going to do is introduce matrix vector form. Remember, in the previous lecture, I discussed how linear algebra is going to be a really important really important concept throughout the course, because we have multivariate statistics. So whenever you have linear models with multivariate data, matrix vector form and operations in linear algebra are going to be absolutely critical. So what I'm going to do now is to introduce some notations. So okay, so this is, we're first going to have a p-dimensional parameter vector b here. Then we're going to have a matrix here. Okay, where each, and this is where the notion of like knowing the sample and the coefficient indexes, the sample and the covariate index is important, where the ijth entry corresponds to the ith sample and the jth entry. And then we're also going to have a vector. I'm going to then we're going to have our data here, where we're going to have our y as an n-dimensional vector. So what we have here is our data here. You can think about now the data in a matrix form. So we have our data here is like x and y, which you can think of as an n by p matrix and an n-dimensional vector. So it's storing exactly the same information, but we're moving from the scalar notation to the vector matrix vector notation. And then we have that our parameter of interest here is b, which is an r to the p, is now a parameter of interest. And then if we look at our statistical model, which is the linear model, you have that this can be expressed as y equals xb plus epsilon. Epsilon now is also an n-dimensional vector, which is going to just be okay, and then we have the whole vector epsilon is 0. Okay, and so now let's think about the estimator or algorithm. You can re-express the least squares equation. So remember that the least squares formulation was like this. So we can now re-express that in matrix vector form in a much more concise way. Okay, so I've introduced another little bit of notation here where where we're using this notion of a squared norm, which is just the sum of I equals 1 to n of vi squared. So there's a lot of potentially new notation here, but all we've done here is converted to matrix vector form. And if things are not completely clear to you, I encourage you to pause the lecture right now and to try to write this out yourself in converting from the standard, the scalar form to the matrix vector form. Okay. Okay, now so let's try to so once again we can find b hat using a very similar principle to what we did in the simple linear regression case, which is to differentiate. Once again, I would ask that the best way to learn is to actually pause the lecture here and to try to do this yourself. This is a little bit more involved in terms of getting your head around the notation because we have now matrix vector form. But I would encourage you to spend 5 or 10 minutes to do this yourself to make this a more interactive experience and to make sure you really kind of understand what's going on here. So if I were you, I would pause the video lecture right now and spend 5 or 10 minutes to actually calculate beta hat. So okay, so I'll give you guys a few minutes to do that, and then so you should pause the video and then we'll return. Okay, so now let's go through this calculation, and what we have here is you're differentiating with respect to b, which is a p-dimensional vector. So it seems like you have to do p different differentiations, but in matrix vector form, you can actually kind of do this, use simple operations of linear algebra here. So if we want to take the derivative here with respect to the whole parameter b, this is actually something we can do very easily. So we want to just take the derivative and set it to 0. And we can actually do that, and that just gives you... And again, this is something that if it's not clear to you how to do this, and it's perfectly understandable that it isn't, I would actually sort of spend some time just going through this yourself. So hopefully you got to this kind of nice, clean way of expressing this. And so what that gives you is you have this expression that x transpose x beta hat is equal to x transpose y. And these are actually referred to as the normal equations. And because like least squares is probably the most solved or the most widely used optimization problem, so getting to these normal equations probably comes up like in billions of different problems in thousands and millions of different people's research. So that's why it's kind of been given a special name. And there's lots of there's basically like mountains and mountains of work going into how to actually solve this problem, or how to actually to get a solution to this problem. And so we're going to talk a little bit about some of those in the next few lectures, but for now we just have these normal equations. Okay, so another way to interpret this is that we have we can if we divide both sides by n, and you'll see why we do this shortly. What you can actually interpret this as is that we actually have a really nice interpretation of what these normal equations are. So you have that if we introduce this notation sigma hat, which is x transpose x over n, and then rho hat xy, which is like the correlation between the correlation vector. Because we've normalized and standardized everything, what this what we can kind of say about this is that sigma hat jk, which is, so this is so let me just explain this a little bit more. So sigma hat is a p by p matrix, so it's x transpose x over n. We have that sigma hat jk is actually the correlation between xj and xk. So normally it would be the covariance, but because we've standardized, so we've centered the variables and normalized them, this is actually just the correlation between xj and xk. Okay, and similarly, if we look at rho hat xy is a p-dimensional vector, we have that rho hat let's just use this notation. Rho hat j is just the correlation between xj and y. And so the way to interpret this these normal equations is that we have sigma hat b hat equals rho hat. Yeah, I think we'll use rho hat xy, but and so what that kind of means is that the regression parameter is basically you just multiply by the sample covariance, and then you get the sample correlation, and then what you get with that is the sample and that equals the sample correlation between x and y. Okay, so now if this sigma hat is invertible, and what that basically corresponds to is that the rank of x is equal to p. so there's no degeneracy in the sample matrix. We'll actually see settings where this is not true. And that's why I've started with the normal equations, because the normal equations doesn't assume anything about invertibility or that there is a unique solution of this expression. Then we can actually just invert it to get a unique solution. So beta hat equals sigma hat inverse times rho hat xy. Okay, so the way to interpret that is that beta hat j is equal to so you basically take the correlation vector and multiply it by the inverse of the sample covariance matrix and take the jth coefficient. Or another way to interpret this is to be no, I think that's a little bit too much to get into today, so I won't go into that today. We'll come back to that later. Okay, so this is how we'd interpret this, and now let's revisit something that we focused on in the bivariate case. Remember that when p equals 1, we had that beta hat 1 equals to rho hat xy. Okay, and so so what about for general p? Does this conclusion kind of say... does this conclusion kind of hold? And the answer, as you can hopefully see, is no. In fact, so what we have for general p, we have the beta hat j, we have the rho hat xy there, but we in fact now have to multiply this by this j. So another way to interpret this is that our b hat vector is just sigma hat inverse times rho hat. So we have that so we need to actually multiply by inverse covariance or correlation matrix. So therefore, beta hat, or b hat, we'll use the notation b hat here. Beta hat is not equivalent to rho hat. So what we see here, and what we're already seeing, I mentioned in the first lecture how going from p equals 1 to general p introduces some challenges and some things that are a little bit different. And this is the first key difference and probably the most important key difference. So if you take anything out of this course and like anything at all, I would say this is the single most important point to take out of the course, and we're going to kind of see this come up frequently in different settings throughout the course. When p equals 1, regression and correlation amount to the same thing, basically, that you only have two variables to worry about, x and y. So the regression coefficient is basically just the same as the correlation coefficient if you normalize properly. On the other hand, for p variables, when you have many variables, The regression coefficient and the correlation values are not the same. So whenever you see regression coefficients with more than one variable, so if p equals 2, p equals 3, so on, the regression coefficient is not the correlation between x and y. And that's a very simple interpretation mistake that people make. And that's one of the key points that I want you to take out of this course, is that they're not the same thing. Okay, so and this relates to some of the points we saw with the two examples in the previous lecture, that now once you start to have more than two variables, when you have three variables, you saw that, there's weird things that go on depending on what you condition on and what you don't condition on. And that's exactly what's going on here. Okay, and so what is the interpretation now? Because I've already told you that we cannot interpret this sorry. Wow, yeah, so we cannot interpret this as the correlation coefficient, as the correlation between xj and y. So we know that it's, not the correlation. xj and y, but it is actually something, but can we relate it somehow to something else? And the answer is that yes. What it is that okay, and so this last key point, as I said, is it's right at the end of this lecture, and I really want this to kind of sink in. So, and again, if you don't get what I mean today, that's okay. I just want to make sure that I mention it now, so that by the end of the course, hopefully this point just really resonates with you. Beta hat j actually does not represent the correlation between xj and y. What it represents is what's known as the conditional correlation between xj and y, given all of the other variables. So for example, if you're looking at a particular, variable of interest and seeing what its relationship is to the response y, what the regression coefficient measures is if you condition, or if you know what happens to all other variables, then what is the correlation condition on this? And this is really important, and why the regression is sort of, in some sense, a more useful tool, I would say, than correlation. Because if you imagine that you have, say 3 or 4, say you have 10 variables of interest, and you want to say the effect of one of the variables on y. If you purely measured the correlation, that correlation that occurs between xj and y could easily be caused by some other by the fact that xj might be really correlated with another variable. But what beta hat j, or the regression coefficient, tries to get to is that if you kind of condition on the others, what is the direct effect between xj and y? And so I've explained that reasonably vaguely, and we'll hopefully put a little bit more mathematics behind it in the lectures to come. so the beta hat j, or the regression coefficient, is really trying to get closer to a direct effect between xj and y, rather than just a simple correlation, which really just says is there some association or correlation. It doesn't get to the question of, if you change xj, is that going to change y? Because maybe the change maybe if you change, even if there's a high correlation, that doesn't necessarily mean that xj has a direct impact on y. And as I said, the last sort of 5 minutes that I've been talking, that's really one of the key points to get out of the course. And I'm mentioning it early on. We'll hopefully see this and understand this distinction more and more throughout the course. Okay, so thank you. That's everything I'll be covering today, and we'll be going into more depth on multivariate linear regression and algorithms, and more on the analysis side of things in the next lecture. Okay, thank you very much.